happy to have with us Professor Ness Shroff from Ohio State University today. Many of us know Ness for many years, and several of us have worked with him. So he is in the chair position at Ohio State University, and he's an eminent scholar there. Before that, he was at Purdue, where he was directing the Center for Wireless Communication Networks that they had there. He's also, since 2009, a guest chair professor at Tsinghua University, for those of you, and there are several, but they are from China. He is very well known in his research in communication networks through the years. He's been here at least once more.
At least one.
And we've been where he is several more times because we have several joint projects. He's a fellow of the IEEE, and he has received, he was a past editor of the IEEE ECE and CSE networking, and of the IEEE communication letters. He has received several awards of his work, most notably several from Infocom. And today he's going to talk to us on low complexity scheduling policies for achieving throughput and delay optimality in OFDM downlink systems. Professor Shroff.
Thanks very much, John. It's a pleasure to be here again. And Arman, I was giving you a hard time because I expect you will reciprocate in kind. This is joint work with some of my present and past students. Bo G is one of my present students, and Gagan Gupta and Shaljin Lin are some past students. So I think for this audience, these first couple of slides are going to be somewhat superfluous, but nonetheless, just in case there is somebody from, I don't know, from solid state here, maybe we can.
Or mechanical engineering.
Or mechanical engineering. So briefly talk about this. So clearly, I think all of you know that the current trends in wireless networks is that the smartphones are generating enormous amounts of traffic in at least an order of magnitude more than our sort of previous not so smart versions. And with smart devices such as tablets and iPads and so on, this problem is just getting much worse. And so it's quite natural that any wireless network that we are going to build in the future will have to deal with much, much larger volumes of traffic. And so the first challenge is how do we significantly, how do we sort of handle these significant traffic loads? How do we expand our throughput region? How do we use it in an efficient fashion? And here are some current trends in sort of wireless systems. As you can see from this graph, if you look at sort of the global traffic in terabytes, there was a time in 2007 where it was dominated by voice, and now data plays a very, very large component in that. In fact, much more traffic has become data-oriented. And moreover, this traffic that's being generated is being generated by a variety of applications that are motivated with this fellow. And these applications tend to have all kinds of different constraints, one of them being timeliness. So there are some stringent delay constraints that one needs to take care of. So the second challenge is that the network must not only provide high throughput, but also provide some delay guarantees or some sort of good delay performance. So if we look at the delay problem, as many of you know, it's a hard enough problem in a wireline network, because the arrival processes are random, and beyond sort of some basic results that we know that have been around since several decades, it's been hard to make progress on these problems. And this gets compounded by the fact that in a wireless network, the channel itself, because of fading, is time varying. So for example, it's not only that delays occur because packet sizes might be different, but now delays occur because the channel itself might be available, might be unavailable, might be available at a lower rate, etc. And this problem gets further compounded in sort of these 3G sort of systems where scheduling decisions now not only depend on the channel rate, but also on the queue length. So the service process potentially becomes even more unpredictable. And what's kind of interesting is that some of the techniques that people have used in the past to achieve very good delay performance, such as opportunistic scheduling, which have become sort of the staple of 3G, 4G wireless networks, actually hurt delay. So, it's kind of ironic that I have this curve, because this is a somewhat similar curve that I presented when I talked about opportunistic scheduling, 7, 8 years ago when I was here, where the basic idea is that, if you want to maximize the throughput in this system, what you want to do is you want to exploit the fact that, you schedule user 1 when its channel condition is best, then you schedule user 2, and then you schedule user 3, and these times over which you schedule could be long enough such that by the time user 3 gets a chance to schedule, it's waited for a very long time. So basically, if you want to increase throughput, you have a problem that the delay increases as well, and this is a real issue. And the throughput delay trade-offs, in a sharp way, for these types of mechanisms are not trivial to characterize. They're quite hard. So one big challenge, which we have already sort of talked about, is can we achieve both high throughput and good delay performance in certain types of systems? And what I am going to try to convince you of is that at least under certain settings, we have some positive results. Okay? And the key insight is that we are now developing, especially in the cellular domain, in the 4G domain, multi-channel kinds of systems which allow us to exploit frequency diversity. That in turn allows us to not only get good throughput, but also potentially avoid the pitfall that I just explained with opportunistic scheduling. So let me spend just 2 minutes kind of describing this setup. So if you look at the left-hand side, this is kind of a traditional TDMA wideband CDMA system, okay, where one sort of wideband channel, typically 1 meg to 5 meg, is assigned to one user at any given point in time, which means that a user needs to wait for many, many time slots before its channel becomes good, potentially. Right? So if you're doing opportunistic scheduling, you have to wait for a long time until that channel becomes best, and then you kind of assign it to the user. But in the OFDM system, the story is a little bit different and perhaps a little more interesting, because the same amount of bandwidth, potentially, can be divided into a number of narrow sub-frequency bands. And therefore, you have an opportunity that each of these sub-frequency bands can be, which are relatively small, can be independently scheduled to different users. So this splitting of the bandwidth is exactly what frequency diversity does, and it helps in basically scheduling, with different users, so that not only can you make throughput, but you can also partition the bandwidth in a way in which, the delay, the user doesn't have to wait for that long to get good delay performance. The other thing in sort of these OFDM systems that we find is that each of these narrow subbands, if they are small enough, they experience flat fading typically. So the fading is flat across these bands. But across the subbands, the channel conditions could be quite different because of multiband. So this has 2 implications. The first one is that if, let's say, a user is in an overall favorable kind of conditions, right? What that user will see is that user will end up seeing lots of sub-frequencies that are in good condition. But even if the channel sort of is not that great, the user has an opportunity to see at least some subbands that are good that could be assigned to it. Okay? So this is sort of one sort of approach in which if you schedule users in these different subbands with favorable channel conditions, the idea is you can perhaps achieve very high throughput without encountering sort of the pitfalls of these large delays. Now, let's assume that this grand research challenge of throughput and delay can be solved. You're still not done, because a big problem with these 4G types, OFDM type of systems, is that the transmission time interval in which scheduling decisions are to be made is typically very small. This is called the TTI intervals. And so the scheduling cycles are relatively short. They're like of a few milliseconds. And at the same time, you have to deal with hundreds of orthogonal channels that you need to schedule, which means that, you know, even if you have a very high complexity algorithm that achieves throughput and delay optimality, it's not enough. So a big design component of our problem is to develop, you know, as low complexity algorithms as we can. Okay? So therefore, the overall goal of this talk is to, you know, move in the direction of developing a unifying framework for designing, you know, practical low complexity scheduling policy that can provide both good metrics of performance in terms of throughput and delay. And of course, from the throughput perspective, there has, you know, been a lot of work over, you know, spanning a couple of decades, starting with, of course, the original work that I'm sure most of you are familiar with by Tasiudas and Efremides on the max rate scheduling, back pressure routing, which, you know, in the early 2000s or mid 2000s, you know, resulted in this, you know, other sort of, you know, a beautiful mathematical decomposition technique which allowed for, you know, cross-layer network control. And since then, there has been a plethora of works which are not going to, you know, thousands of papers have been published on this literature. So the feeling is a throughput problem, at least from a, you know, high complexity sense, is fairly well understood. Okay? Now, let's think of what has been done in the delay problem. There, the works have been relatively limited. And they've also focused mainly on single channel systems, so that people have not looked at multi-channel systems, except for a couple of references that I'll talk about later. And I sort of classify these works in these 5 different domains. There is work on heavy traffic, there is work on large buffer, large deviation asymptotics, there have been this work on method of Lyapunov drips to get expected upper bounds, system-wide lower bounds on the delay, as well as works on sample path optimality. And each of these have their pros and cons, and we can kind of discuss that perhaps, you know, I think it's instructive to talk about these, but perhaps at the end of the talk we can kind of go over them a little more. But the main point I wanted to make was, look, all of these works that I've described ahead focus on single channel systems, and what we are looking at is multi-channel, but in the cellular context. And so here is now the basic outline of the rest of the talk. What I'll do is I'll spend a few minutes talking about the system model, then I'll define a metric for delay optimality, which is the large deviation rate function optimality, where what we'll do is we'll derive some sufficient conditions for that. Then we'll talk about throughput optimality and again derive some sufficient conditions. And then from both of these sufficient conditions, we'll show how to come up with a low complexity hybrid policy that achieves our objectives. And then we'll say, well, look, that's fairly low complex, but perhaps can we do even better? And then we'll look at some complexity performance trade-offs, and then finally, So here is the basic system model, without putting sort of mathematics in it yet. So as I mentioned before, we are looking at a multi-channel system like an OFDM system. So our focus is on the downlink of a single cell in such a system. So we consider a wide band that can be divided into many, many narrow subbands. Let's assume they have n channels. And let's assume that there are many mobile users. And everything that I say can be analyzed with a constant times the number of users, but I'm just going to assume for the rest of the talk that this constant alpha is 1. And we assume a very simple channel, and then we'll talk about sort of some of the assumptions we've made and how to relax them at the end, also describe them, which is an on-off channel, which basically says, look, at each time slot, each channel is on for a user with a probability Q independently of the others. And we assume that the base station knows this information. So we assume that the base station has perfect channel state information, which can typically be achieved by the base station broadcasting a pilot signal on all of the channels in parallel, and each one of these receivers, based on the pilot signal strength, can measure their SINR. If it's above a certain threshold, they transmit back a 1. If it's below a certain threshold, they transmit back a 0. So it's a very simple kind of 1-bit kind of operation. And it is instructive that we look at this cellular system in the context of a multi-channel queuing system with time-varying connectivity. Okay, so if this you can do if you end up viewing these channels as servers. So now let's look at this system as really a bipartite graph. Okay, and in the bipartite graph you have queues that are at the base station, and each queue corresponds to a particular user. Okay, and what the base station needs to determine is which channel to assign to that particular user, or set of channels to assign to that particular user. That's the decision that the base station needs to make. And a channel or a server S, okay, as defined by the principles of the multi-channel system, can only serve one user at one time. So a subband, so we're calling a channel a subband, right? Can only serve one user at one time. But a user can get service from multiple channels. So keep that in mind. Now we assume that the arrivals are IID across users, but correlated across time. So they can be correlated across time. And we'll talk a little bit about how we can even relax the IID across user assumption. I already talked about the fading model, which basically means that each channel is on for a particular user with probability Q independently of the others. And so the red edges at any given point in time are showing the true connections. That means, in this particular case, mobile user 1 can be connected, to mobile user n, okay, because that is a red edge. That's pretty sure. So as I said, the base station allocates users to a particular channel. That's the scheduling decision to be made. And if the channel is on, we assume that a packet can be transmitted in that time slot. Now this is another thing which does not need to be one. You can have a multi-rate, so you can have multiple packets. But for the purpose of this talk, we'll assume that one channel, one packet. And as I mentioned before, the analysis holds true if the ratio of the number of users or the number of channels is a constant, so it doesn't have to be n to n. Yes, go ahead.
So even if I fix a particular user, the channels are completely behaving independently, even for a fixed user?
Yes,
okay.
yes. So basically, the assumption is that there is some kind of guard band that sort of decorrelates it because of multi-band. It's an assumption. And we'll talk about that. In practice, if the frequency bands are close enough, there is still some correlation, clearly. But that's the assumption that we need for the delay analysis. All right, and so it's not clear that it would provide either an upper or a lower bound. But interestingly, what we can do is if you relax that condition, instead of getting optimality, you can get upper and lower bounds on the performance. So there is that. Anyway, so the objective is to maximize throughput. That's the first one, which I think everybody pretty much understands. The second objective requires some more explanation, which is we'd like to sort of minimize the delay. So we assume that all of the traffic has the same deadline. Okay, let's assume that the deadline constraint is B. And then what we would like to do, ideally, is we would like to minimize the probability that the maximum head-of-line delay exceeds this value B. Okay, so this is something that we would like to analyze. Of course, those of you who work in queuing know that analyzing this problem in its exact form, even for a single queue, is an open problem. So we do what we can, and so we look at the problem in an asymptotic regime where the number of users is very, very large. And so what we are going to do is we're going to maximize the rate, large deviation rate function in the many user, many channel asymptotic. So the idea being that if we maximize this rate function I of b, we will end up minimizing this when n is sufficient.
This depends on the scheduling policy.
Yes, this depends on the scheduling. So the scheduling policy, we need to choose a scheduling policy in order to maximize. So now let's talk a little bit about some related works on the multi-channel system. There are two key pieces of work that are related to this discussion. One is this very nice work which actually focuses directly on delay, where Sharma and Lin have produced this delay-weighted matching policy, which turns out to be rate function delay optimal, as in the sense that we talked about. And although they don't show it in the paper, it's fairly easy to show that this is indeed a throughput optimal policy. Okay? However, the complexity is somewhat high. It's n to the power 5. Right? So whenever you see a polynomial of the order 5, you always worry about the complexity. So that's one problem with that. Then there is this other work that has been done by Shakotai and others, which they've tried to look at an approximate metric of delay, which is the Q-length metric. However, what we have found, and what is not that unobvious, is that getting good performance in terms of the Q-length actually does not translate to good performance in terms of delay. And also the Q-length based optimality is known for in their case, for a very restricted arrival process, which is IID in time. With the tools that they employ, it's very hard to see how you can generalize it. It appears that it's sort of very, very restricted. So that's sort of the related work. But still interesting, and we will talk about some ideas that we use from both of these papers. Yes?
Can you add a few words about what is it about their method that makes it n to the 5?
I'll describe it actually. In fact, I'm going to talk about it in quite a bit of detail.
Oh.
So here are some, just very quickly, assumptions for throughput optimal. Yes, go ahead.
If you're going to let n run to infinity, then in your error criterion, you have the maximum over all i's running between 1 and n. Now then, in the asymptotic is one small guy who's messing things up. Is that a good performance measure, or should you be taking averages inside? Can the average problem be solved rather than the maximum?
So you mean an expected?
No,
you mean the sum?
Yeah.
So there are some results in a different context that show that when you're trying to maximize the sum, okay, it's going to be dominated by that guy anyway, by the max. So in that sense, when you're looking at n goes to infinity, you won't see much of a difference, because the dominant value is the max value, right? So that's the decay rate. So you're stuck with it. But that's a good point. But what you'll see is actually, from a practical point of view, this actually gives fairly good results, as you'll see through simulation. So the assumptions on throughput optimality are sort of the standard assumptions that one needs when one is working under fluid limit types of arguments, so nothing new there. For rate function delay optimality, we need a little bit more. We need that the arrivals are bounded. So it doesn't matter how large the bound is, but we need bounded arrivals. And we also need, as I said, IID across users. The mean arrival rate is P for all I. And we need this relationship, which is sort of a large deviation relationship, which roughly speaking says that, look, when n is large, the probability that the aggregate arrivals strays away from its mean, okay, is relatively small. It's kind of vanishing exponentially. All right, so, by the way, so essentially the kinds of conditions of AI that satisfy the second condition are clearly IID and also described by traditional sort of Markov chains. They kind of work fine, like on-off models, multi-gate Markov chains. They something like this. essentially, I mean, we haven't proven this for a fact, but essentially, anything that's short range dependent, I believe should hold true, although we haven't proven that. Okay, so before I get into some of the details, let me give some intuition on how to get delay optimality. And this intuition is going to start with the very simplest model. So let's assume that you have a single server system with fixed capacity. So now the capacity is actually, forgive me the information theorists, I mean capacity in a networking sense. So in this particular case, a first come first serve policy, okay, serves the oldest packet first. So this policy is obviously delay optimal. Now let's look at the many user, many server system where you have full connectivity. So let's assume that this Q probability is equal to 1. Everybody is connected to everybody else. Then you can construct an analogous single user, single server system. Okay? And then basically what happens is you end up serving up, the ones with the largest head of line delay first, and that is also delay optimal. That should be fairly obvious. Right? Sort of like earliest deadline first. So now let's look at the scenario where you have many users, many server systems, but now you have time varying connectivity. And the question is a policy that schedules the oldest packet first still delay optimal? And clearly, if you can have a policy that schedules all n, okay, if there are n servers at any given point in time, oldest packets, as in the case with full connectivity, then that policy is always going to be delay optimal. It's delay optimal even in the fully connected case. However, this may not be feasible, right? So you might have random connectivity at a given point in time. For example, Q1 now, which has the 3 oldest packets, is not connected to server 3. Okay? So there's no way you can actually do this. This is simply not a feasible policy. You cannot serve all 3. Right? So then the question comes, okay, can we compromise and say that a class of policies that serve the k oldest packets for the largest possible value of k that's given by the connectivity structure that you have right now, is that going to be optimal? And it turns out that that is indeed the case. And in fact, that gives us the first sufficient condition on rate function delay optimality. So basically, this theorem essentially says that under assumptions A2 and A3, a scheduling policy which falls in the class of scheduling policies P such that it can serve the k oldest packet in the time slot for the largest possible values of k among all possible values of n is indeed a delay function optimality policy. And the proof is actually based on some arguments in the work by Sharma and Lin, where they've kind of defined a particular scheduling policy called the FDS policy. And what we show is we show a dominance over that particular policy. So we define, based on the sufficient condition, we define the class of OPF policies, or oldest packet first policies, that essentially satisfy this condition in theorem 1. So it basically tells you this. Okay? If you have full connectivity, well, it's going to choose packets 4, 5, and 6 to transmit. So these will be connected to server 1, 2, and 3. If you have partial connectivity, then what it's going to do is it's going to, so for example, in this case, Q1 is not connected to server 3. It's going to choose packets with head of line delays 5 and 6 to see. So in example 2, the key point is as long as the 2 oldest packets are satisfied, the sufficient condition is satisfied. Okay, so we don't have to worry about the fact that in this case, Q2 could have been served by S3. Okay, a scheduling policy that even ignores that will still be rate function delay. All right. So
So
now
it's assumed that the cell knows
the channel condition.
without delay on the information about that.
Yeah. A perfect channel, like say on-off kind of perfect channel.
But I also know it at the same time.
Yes.
Nothing is changed.
Right now everything is, yes, go ahead.
Can you go back one slide?
Sure.
So in the bottom right figure, if Q2 had a packet with delay 4, then you would need to route that, right? Because then there would be 3 packets, 4, 5, 6 that could be routed. Is that correct?
So if this one had a 4 on it,
Q2, yeah.
right? Yes, exactly. Because all 3 could be routed potentially. Okay. So now we go to the delay weighted matching policy that was proposed by Sharma and Lin, and it's instructive to look at this policy because indeed it's a class of OPF policies, and we'll see why. There was a question that was asked, right, why that policy has a high complexity. So this is what they did. Okay, so this policy, okay, what it does is it maximizes the sum of the delays of the packets that are scheduled at any given point in time. So in this case, in this example, the sum of the delays that it maximized will be depending on the configuration that you have. So it basically means that packet 6 is chosen, packet 5 is chosen, and packet 3 is chosen. Right? So these are the 3 packets that can be chosen to maximize the sum. And as you can see, we haven't stopped here at 6 and 5, we are also scheduling packet 3. So it does a little bit more than the OPF requires. Right? Now, the way it can be implemented is to do a maximum weighted matching, okay, over an n squared by n bipartite graph, okay, which results in this order n to the 5 complexity. And I'll show you how this is done exactly. So let's assume that you construct a graph which has 2 vertex sets, L and R, okay, and 1 edge set E. So the vertex set L corresponds to the n oldest packets of each of the n queues. So it corresponds to a total of n squared packets. It's taking n oldest from each of the n queues. Right? And so you can see that the n oldest in this particular case turn out to be 6 and 3 from the first one, 5 and 1 from the second. Right? And now the vertex set corresponds to n servers. Okay? And then you define an edge set E, okay, to have an edge between the 2 vertex sets if the queue containing the packet in question in the set L is connected to server R. So for example, what you have is in the first queue, since the first queue is connected to both servers, you have an edge between 6 and 3 and both queues. In the second queue, since it's only connected to server 2, you only have an edge between 5 and 1 in this. And then what you do is you define the weight of an edge, okay, to correspond to the delay of that packet, the head of line delay. And then you do a maximum edge weight matching. Okay, so this maximizes the sum of the weights of the edges of the matching. So that obviously for a bipartite graph is going to have complexity on the order of n squared because L itself is n squared, right? And E, okay, the number of edges in this case has to be n cubed, right? So it has n to the 5. So that's how the operation works. So motivated by this, very kind of nice structure that they have, but complex structure, let's think of how one can get another oldest packet first policy, okay, but with lower implementation complexity. So what we do is we look for simpler OPF policies by doing the delay weight matching, but now instead of looking at it over the n squared oldest packets, we are now looking at it over n packets. Okay. So now what we are doing is we are maximizing the sum of the delays of the packets scheduled over the n oldest packets in the system. Okay. In this case, the first thing that we have to do now is that these are over the whole system, right? So we basically need to find these n oldest packets. So you can imagine that itself is a sorting operation, right? That we need to do. But just to quickly say this implementation results in much lower complexity. It's order n to the 2.5 log n. And the way we will do this is instead of doing a maximum edge matching, we'll do a maximum vertex matching, which helps reduce the complexity slightly further, okay, over an n by n bipartite graph. Now it turns out that they didn't use a maximum vertex weighted matching because they didn't know about it. We could use it on DWM, but the complexity reduces only from order n to the 5 to order n to the, I think, 4.5 if you do it that. All right, so here is the operation. We define a vertex set L again, which corresponds to the n oldest packets in the system. And now instead of assigning weights to an edge, we assign weights to that vertex set. So that's basically corresponding to the delays of the packet. Now, as I said before, forming this vertex set itself is an order n squared log n.
Is the same as before?
Sorry? This is n squared log n. This is the sorting part.
The L is the same.
Sorry?
The set L is the same before.
No, it's not. Right? The vertex set L is now only the n oldest packets. In the other case, it was n squared oldest packets. That's the big difference. And now the vertex set R corresponds to the n servers, and the weight of all of those n servers is simply denoted to be 0. So we just give the edge weight, the vertex weight for set R, or for all its components to be 0. And then we say there is an edge between L and R of the queue containing packet L is connected to server R. And now what we do is we run a maximum vertex weighted matching. So that means for any matching, we want to make sure that the sum of the vertices is maximized. So why is there a matching? There's a matching because of the fact that you have to worry about the fact that one server cannot be allocated to 2 queues, right? More than 1 queue. So that's why there's a matching. The same thing over here. That's the reason. So this is why you get, and this operation, this MVM operation is order n to the 2.5 log n. So you sum these and this one dominates. And that's why you have an order 2.5 log n. Okay. So it's pretty, I think, easy to see that DWMN is at least oldest packet first, right? It's going to choose at least those. And therefore it's delay optimal in the large deviation sense. Okay? However, what you'll see very quickly is that DWMN is a lazy policy, which means that it's wasting some possible schedules. So let's look at what happens here. So in this case, I have this system, okay, and what DWM does is it considers it's maximizing over the 3 oldest packets, right? So it's looking at packets which delay 6, 5, and 4, okay, and therefore it's finding that since Q1 is connected to S1, it can only serve packet 6. Okay? And so it ends up not being able to serve, for example, packet 3 or packet 2, and so clearly it's idling. Right? So even though when this policy is optimal in a rate function point of view from a delay perspective, it's not clear whether it's true or
Why
not.
will not serve the last 2?
Because that's not the policy. Right? The policy basically says that it's looking at the n oldest packets, right, and determining the schedule based on that. And you can see that in this queue, okay, only 6 can be served, right? 4 and 5 can't be served. So it's basically blocked, right, at any given point.
But the others are independent, right?
Sorry?
The other queues are independent.
I understand that, but then you have to search, you have to have a policy that schedules them as well. That raises.
Is that an artifact of the fact that we have n and n?
I'm sorry.
The numbers n and n are the same.
Oh no, but you can construct it similarly, right? It's not. That's not the artifact. I mean, it is for this particular model. But, you can, as long as they're they're constant, a similar thing will happen. Basically, as Arman said, you have head of line blocking. That's essentially what occurs. It'll occur with many scheduling policies. Okay? So this one is one which is able to maintain the oldest packet first property, Okay, but still, and so therefore it is delay optimal, but the question is whether it's throughput optimal, and it may not be. And in fact, we can easily show that this is not throughput optimal by constructing sort of patterns, arrival patterns that kind of fit this, even in a stochastic way.
When you say it's not throughput optimal, you mean
On a finite n. That's the difference.
On a particular sample path? Or
No, you can actually come up with more than a particular sample path. You can come up with a probabilistic kind of construction for which it is not.
And throughput optimal here means again the same?
Yes, the same as it always
So
is.
the twos are stable.
Correct.
So you're not really asking much.
You're not really asking
No.
much in that sense, right? So it is so essentially. So this is a very sort of a good sort of thing to kind of dig deeper into, right? How can something be delay optimal and not throughput optimal, right? I was telling John this morning that you cannot have delay optimality without throughput optimality, right? Typically, right?
Which said disagree?
Right? Sorry?
Which said disagree?
No, you did agree when I gave you the example, right? Let's get into that later. Yeah, I understand. But what okay.
That's why I wrote it down.
Yeah, fine. But what I'm trying to say is that look, the rate function optimality, remember, is when n becomes very large. Okay, and when n becomes very large, when this policy B is throughput optimal as well. Okay, but
The other question I
the
had
point is, I just want to finish this point. So the point is that typically these large deviation rate functions converge pretty fast. Okay, so you kind of converge to the rate function pretty fast. So even if that were to happen, the throughput may be poor for small to moderate size. That's the issue. Okay, so that's why throughput optimality is still something that needs to be looked at in addition to the large deviation rate. Yes, Sanjay.
So you say the rate of convergence in the relativization result is pretty fast.
Typically, and that's people know from queuing that that we are talking now only about the slope. Right? It may not converge to the right constant,
Right,
but
but
it converges.
relativization results when applied to networks,
Right.
the rate is actually depending on the network topology.
The what?
On the network topology you assume.
True, but you
Unless you assume regular graphs or regular topologies.
I don't even know what that means actually. I mean, so you're talking about a network of queues?
Yeah.
Okay, yeah, but here you don't have that, right? You have a sort of a multi-server
That's what
kind
I
of
see.
system. I agree. I mean, there are issues. So it'll be dominated in a network of queues by the bottleneck queue, right?
Right.
Whichever queue is the bottleneck queue will give you the worst sort of large deviation rate function. All right, so now let's shift gears a little bit, and now let's look at throughput optimality. Okay, and of course, if we have to look at throughput optimality, we have to look at the algorithm that was created at University of Maryland, not the least of which I'm giving a talk at University of Maryland, but nonetheless. So let's look at the max rate scheduling algorithm as it was defined. So in our context for this multi-channel, multi-server system, this queue max rate scheduling algorithm, which is the traditional algorithm, it depends on the queue length rather than the delays. Okay, basically says that at each time t, each channel or server serves a user with the longest queue length. Okay, and this you can use stochastic Lyapunov techniques to show that this algorithm actually turns out to be throughput optimal. However, it's instructive to be able to prove this throughput optimality also through this domain of fluid limits. Okay, and I won't go into the details of fluid limits except to say that fluid limits correspond to a sequence corresponds to the limiting process of a sequence of processes. Okay, that are scaled by this value r, for example, in both space and time. Okay, so in a certain sense, what it's doing is it's removing some of the stochasticity in the system. So it's easier to handle, for proving purposes. It's easier to prove things in the fluid limit. So if you can show stability of the fluid model, typically you can show the stability of the original stochastic network, and this was shown by this paper by Dye in '95, and then later on, Sasha Stolia looked at this problem for discrete kind of time in a more general, if you look at Dye's paper, he needs some conditions actually which are quite restricted, which I wasn't initially aware of before I started digging deeper into that paper. And so Stolia's paper removes a lot of those restrictions. So the insight that comes from this is in proofs, it's sufficient to choose scheduling policies that are max weight in terms of the queue length and the fluid limit. You don't have to worry about just being max weight in the actual stochastic system. Now, another reason why the fluid limits are useful is because the delay-based counterparts of max weight schedulers cannot typically be proven through these traditional stochastically above techniques. At least I haven't seen that. It has been typically shown to be throughput optimal using fluid limits. In the static setting for single hop traffic, it was shown by Andrews and all. And in multi-hop, we showed this with one of my students recently. And also it's been shown in a more general setting with dynamic arrivals and departures by Gustavo De Vician and his students. And the key to the proofs is that when you look at the process and the fluid limit, you get a linear relationship between the queue length and the delay. Okay, so remember, this is just the deterministic version of Little's law. Right? That's basically what it is, right? So that allows you to kind of get like a deterministic version of it, right? And so, again, the insight from the proofs is that to achieve throughput optimality, it's sufficient to choose the schedule, okay, with a maximum weight in the delays in the fluid limit. Okay, so this kind of gives us some possibility that since this fluid limit is sort of is happening in sort of in a limiting regime, perhaps there are many more schedulers for which this can occur, and that allows us to get actually a sufficient condition on what schedulers could actually be throughput optimal that we can use later on. Okay, so this is the sufficient condition. It says that a policy P is throughput optimal if in each time slot, each channel can serve a queue whose head of line packet delay, okay, is no less than that of the nth packet in the queue that has the largest head of line delay. So you don't have to worry about serving the largest packet in the head of line delay, as long as you can show that you serve any head of line packet, and that packet delay is no less than that of the nth packet in the queue with the largest head of line delay, then you're fine. So it kind of expands, in a sense, the class of possible throughput optimal policies. And in fact, what we do is we now define a policy, based on this sufficient condition to be in this class of MWF policies if it satisfies this condition. So this can be used to immediately prove that the delay weight matching policy that Sharma and Lane have is actually throughput optimal. Of course, the delay max weight scheduler, because it's already choosing the one with the largest max weight, so it's also going to choose the same one in the fluid, so it is already. But in addition, it also allows us to prove some throughput optimality of some greedy policies that we will consider.
So this reminds very old stuff which used to be called operational calculus queues, where they were not do stochastic modeling.
This is, so the fluid limit stuff.
Before 95.
Well, could be. I mean, like for example, what's the guy who's at Illinois who went to Florida? Sean Main has,
But even
it's
before
involved.
in the 70s, they said from the point of view of practical networking,
Sure.
I do exactly this time and scale averaging, and nowhere was the distance. And see if you can. And then there was a guy.
I mean, I'm sure that some of these arguments have been around. The question is, under what conditions can you prove these results?
No, because there was what's this guy? He even went to the students in his book. He was asking which ones of the laws, likelihood laws, were not stochastic, and you can actually prove under operational calculus.
Still?
Yeah, it's still okay. Thanks.
So anyway, so let's look at a little bit more about the delay max weight scheduler in the context of our system. Okay, so this basically policy is, doing a scheduling mechanism such that each server serves the connected queue with the maximum head of line delays. Okay, so if we look at this example, here you can see that the head of line delays are 6, 5, and 4. Okay, so all of the servers choose Q1. because that's the one that has the maximum head of line delay. So that means in this particular time slot, all of the servers are choosing 1, okay? And as you can see, one of the, they can only serve 2 of these packets, right? So one packet gets not served based on this policy. And the operation of max wait scheduler actually in this context is very simple. It's an order n operation in parallel, if you think about it. Because all each server has to do is basically find the queue, okay, all right, which find out of the n queues, which one of the queues has the maximum head of line delay. And if this can be done in parallel, you have an order n complexity, otherwise you have order n squared complexity. And clearly we know this is throughput optimal.
So if there is large spread of the head of line queues, then you are in trouble.
You are. So in the worst case scenario, for example, if you have a very large network, right, like a very large N, and let's say, for example, all of the queues are connected. For example, let's take that, right, and then basically only one of them, right, has a sort of head of line delay, which is very, which is the largest among these, right. Then all of the queues, all of the servers will be connected to that. So then what will happen is all of the other users have to wait until the next scheduling cycle before they get served. And that's exactly why the delay performance is so bad. So in fact, what you have is that you have actually a zero rate function, which means that the probability that your waiting time exceeds a certain deadline is actually a constant. It does not decrease when the number of servers actually increases. And basically the reason is that servers make decisions without accounting for each other's decisions. And that's the main reason why this performs well from a throughput point of view, but very poorly from a delay point. Okay.
But
So
the scenario that you described, as the n gets large, has a very, very small probability of taking place.
it's true. So with one queue. But what happens if you, like, for example, assume like Bernoulli arrivals, then you can actually show that you basically end up getting order log n type of queue. So it's still very, very small relative to the. So now the basic idea is the following. Okay, so we have sufficient conditions for throughput optimality. We have sufficient conditions for delay optimality. Can we somehow intelligently combine the right policies, from the class of, let's say, OPF policies and from the class of max weight and the fluid policies to get a delay optimal kind of policy as well as a throughput optimal policy? Okay, and so we have to show that this constructed hybrid policy must at the same time satisfy both conditions, okay, in theorem 1 and theorem 2. If we can do that, then in fact we are done. We basically established what we can do. And so for that, we have the following implementation, and there are lots of implementations which can achieve this, but this is one that I'll talk about, which is the hybrid DWMN, which is, remember, the delay weight matching policy, which doesn't look at all n squared packets, but only looks at n. So this one has a complexity of order n to the 2.5 log n, and this policy, which has complexity order n in parallel or order n squared, if you don't do parallel implementations. Okay. And the way it works is the following. In stage 1, you run DWMN and remove the matched packets and servers. So whatever packets have been matched, you remove them, and you remove the servers, because a server can only serve one packet, right? So you don't take that into consideration. And in stage 2, each of the remaining servers that were not allocated in stage 1, okay, choose to serve the remaining packet using this, delay-based max weight scheduling policy. So let's implement this and see what happens. Okay, so there is the system. In the first stage, server 1 chooses packet 6 because it's looking at the 3 oldest packets, which are 4, 5, and 6. So it's looking at 6. And in stage 2 now, both servers 2 and 3 notice that the head of line queue is 3 here, so they both pick this. And indeed, what you can show is you can show that this hybrid DWMN and DWS policy is both throughput and rate function delay optimal. intuition of the proof is the following, okay? What happens is in stage 1, you guarantee delay optimality from theorem 1, obviously, right? But the allocated servers also satisfy the sufficient condition of throughput optimality from theorem 2. Remember the one where all you had to worry about was make sure that you served at least, the packet with, the delay being, basically n away from the from that of the worst case delay. Right? So that's basically satisfied. And then stage 2, the cool thing is it does not spoil delay optimality because you've really removed that server, right, from the system completely, right? Because in a sense, that server can only serve those packets, right? Otherwise, it cannot serve anymore. So you remove that. Right? And so the remaining servers also satisfy the sufficient condition of throughput optimality. And so the overall scheme turns out to be
So for functions,
go ahead.
You fundamentally what you're saying is that in either dimension you don't do worse.
Yes.
So what is there to prove then?
In what, I'm sorry?
In either dimension.
Oh, no, but when you apply the policy together, right, the problem is that, you might, for example, you can think that, when you're applying a policy iteratively, right, you might be removing some cues in a way in which you might affect the other dimension, right? But because of this reason, this is the allocated servers satisfy a sufficient condition, that's why you don't. It's only about the allocated servers, it's not about the rest of the servers which matter. Because obviously we know that DWMN doesn't satisfy the sufficient condition for the rest of the servers. Right? It's only about the allocated.
So for finite problem.
Sorry?
For finite.
For finite n,
When you're not in the absolute.
correct. It satisfies throughput optimality.
Wait.
Right.
This is like when I do optimization in 2 variables and I do a zigzag approach or repeated projections or whatever you want to call it. Usually there you have to do something to make sure that, as you said in the answer to Arman's question, is that I don't, when I do the first step, I'm not leaving something that's going to affect the second part. And that's how is it guaranteed for finite set, not asymptotically.
Well, through delay optimality is not for finite n, right? It is only in sort of
So when you apply to finite, what happens?
Well, you would expect that you'll still get good delay performance, right? Because as I said, the large deviation rate function typically converges very quickly. You'll see through simulations actually that indeed happens. Right?
So here
But for throughput,
so the coupling here is because of this second line.
Yeah, this is the part, the allocated servers.
That
That's why we needed. That's why I wasted time in a sense on these fluid limit kind
When
of.
you throw them out, you don't allow any coupling that can help you in the second step.
Correct.
So it's almost like a decoupling here.
Well, this is because that's because you're throwing once the server is allocated, it's matched, right? You don't need to worry about it.
Okay.
So now, okay, great. We have a throughput and delay optimal policy, which is order n to the 2.5 log n complexity. What if we want to reduce the complexity further? And so in this case, how much time do I have? I have time? Okay, so then in that case, we can study 2 different types of greedy policies, okay? Which are, one policy is greedy from a delay, from the point of view of the queue, and one policy is greedy from the point of view of the server. And so this policy we are calling delay-based queue-side greedy and delay-based server-side greedy. And the reason why there is this delay-based acronym is because the server-side greedy policy has actually been studied in the context of queue lengths. And then we'll parameterize the server-side greedy policy, okay, to explore a further reduction in trade-off between complexity and delay performance. All of these policies, because of the sufficient condition of throughput optimality, turn out to be actually throughput optimal. So quickly, the delay-based queue-side greedy policy works in the following way. It iteratively schedules the oldest packets. Okay, so what it does is there are multiple rounds in each time slot. Okay, and in each round it picks the oldest packet with at least one available server connector. Okay. And if there are ties, it ends up picking the one with the smallest index. You can do anything random if you want, but that works. And then chooses one of the connected servers to serve this packet, And this is the key thing. It needs to find at least one available server connector, and that requires some complexity. And then in subsequent rounds, it does not consider packets that have already been matched, and it keeps repeating this. And the complexity of this is order n squared with parallel implementation n cubed. So it's a slight reduction in the complexity. Okay, so here is sort of the policy. Here is how the policy works. So you have this system, okay, and in round one, okay, since packet 6 is the oldest packet, it picks one of the 3 servers that it's connected to, in this case, server 1, that has the smallest index. In round 2, the next oldest packet is packet 5, so it picks server S2. And in round 3, it would like to pick 4, but it cannot pick 4. Okay, the reason is that there is no available server connected to 4, so then it picks packet. So that's why packet 4 is skipped. And there is an equivalent policy from a server-side greedy, which is perhaps even simpler to explain, okay, which iteratively allocates servers one by one. So this is what it does. Again, it has n rounds in each time slot. And in each round k, it only looks at server sk. So it's starting S1, S2, S3. And in server sk, it runs delay-based max width scheduler. So what is it doing? It basically serves the connected queue with the maximum head of line, or the maximum delay. And then it updates the head of line delays by removing the match packet. So whatever has already been matched gets removed, and then you go to the next round and so on. And this complexity is order n squared, which should be pretty straightforward to see, right? Because each one of these can do this in order. Okay, so here is the example. Server 1, first picks 6, okay, because that's the one with the maximum delay. Then server 2 picks 5, that's the one with the maximum delay now, and then server 3 ends up picking 3. Okay. So this is basically the this is the greedy algorithm, and as I said, it sort of reduces the complexity a little bit over the optimal solution. So now it's instructive to compare this server-side greedy policy with the max weight scheduler, which has much lower complexity. But before I do that, we have this theorem which says that both greedy policies are indeed throughput optimal. And while we cannot show optimality of the rate function, and I'll talk about that actually at the end of the talk, we can do better than this. We can, at least this theorem tells us that we can show positive rate function. That means the rate function is positive, which means as n increases, this probability is not remaining constant, it's actually kind of increasing. And like in the case of MWS, okay, delay-based MWS, these policies can be combined with the delay weight matching with only n packets, and we can get throughput and rate function delay optimality with the same complexity.
I look at the term 4.
Yes. Sure.
I know that the rate function is 1 and look at the strategies that get there, EQSG, ESG. Which one is the largest IV?
Okay, both are very good questions. The first one is that we need assumptions of the arrival process for the existence of the rate function. For the second one, it turns out actually that both of them, we just showed this actually, pick the same schedules if you use certain tie-breaking rules. So actually they have the same rate. So they actually end up, in fact, we were surprised. They actually end up picking the same set of schedules if you follow certain tie-breaking rules. All right, so now, since we want to do a complexity delay trade-off, let's quickly, looks like your audience is going, should I start wrapping up? Okay, 5 minutes? Okay, all right, so here we're going to compare greedy with max weight scheduler. And what we see is that in greedy we have n rounds, while in the max weight scheduler we have only one round, and that's the main cause of the complexity, additional complexity. Okay. In the greedy, though, we can show positive rate function, while in the max weight scheduler we can only show 0. So there is certainly an improvement in the delay, although both policies are throughput. And the insight is that, look, because you have more rounds in each time slot, you have more updated information. Remember, one of the reasons why the max weight scheduler was not working was because you could potentially, all of the servers could potentially pick a small subset of the queues, because those are the queues with the head of line, largest head of line delay. But because you're doing it in rounds, you're removing those, right? So you kind of do better. So you have more updated information in each round. So you have better delay performance at a higher complexity cost. Okay? So why not construct a parameterized policy, which is basically looking at the integer version of n to the 1 minus alpha. Okay, and so it's reducing the number of rounds, okay, and it's therefore reducing the complexity correspondingly, and of course it's throughput optimal, and we think, unfortunately, with some latest results that we have, that this is actually also has rate function optimality, rate function of 0. Okay, but in simulations actually it seems to be showing some good performance. All right, so here is the simulation setup. Quickly, we are looking at both IID and Markov chain-driven arrival processes, and basically the channel on probability is 0.75. And the first figure, let me explain. The first thing to notice is that the DWMN, which is the delay rate matching policy that only looks at n packets, right, the one that's rate function optimal, actually has the same rate function as one would expect as this very complicated delay weighted matching policy. And so do the greedy policies. They also have the same, appear to have the same rate function optimality. So the question is, can we prove optimality or near optimality for these policies? The other thing is that the delay-based greedy policies, as you can see, are all bunched up here, significantly outperform the Q-length-based counterparts. Okay, so this means that, look, Q-length-based policies are not good if your goal is delay. That's the one thing. And here you can see that the max weight schedulers are terrible, right, as one would expect, because they have 0.
It's no.
Sorry?
It's no.
Is it?
Max weight policies are terrible for delay.
I'm not sure that was actually known. I mean, this is happening because of the multi-channel situation. If it was in a single-channel situation, it's not really true. Anyway, same results for the IID case. I'll skip. Now what we do is we keep the number in the system to be very small, and we vary the deadline. Okay? And now what you see is that the hybrid and the optimal coincide, and so do all of these are bunched in with the greedy policies. So they're all kind of same. But DWMN, that's this green one. Okay, that's the rate function optimal. That's a little bit worse. Okay, potentially quite a bit worse because n is relatively small.
What's the light blue one?
This one are the Q.
The light blue one.
This one, right?
The Q one.
Q-based greedy policies. And again, once again, the delay-based policies outperform the Q-based counterparts. This is some result that we have, which shows that as alpha decreases, you get better delay performance.
So is it fair to say out of this one, you should develop a abstract principle that says if you care about delay, do not use metrics that are based on Qs?
Do not. Yes. Well, at least it seems to be true for the multi-channel system. Okay, so this is a quick summary of the contributions. Maybe I can skip that since people are kind of leaving. And I will. Do you want to talk right now about some of the future work, or I mean?
Finish your talk because it's going to be good.
Okay, all right. So then Okay. So what we've done is we've developed an analytical framework as we wanted to for achieving throughput optimality and delay optimality. We did that by characterizing sufficient conditions in both cases, which led to a relatively low complex. I don't know if people will say order n to the 2.5 is low enough, but certainly better than order n to the 5. Right? Complexity algorithms. Looked at further lower complexity policies, which are sort of greedy policies, and sort of studied some empirical performance of these parameterized space policies. So before that, the only policy that was known was this DWM, which has this very, very high complexity. Now, motivated by the fact that the greedy policies actually appear to have such good performance, okay, we've got some very recent results which I haven't had a chance to check. Okay, so the student has done this, which is why I didn't put it up front in the talk, that in fact they do have near optimal delay performance. So they basically, the performance is, if I star b is the optimal rate function, then what you find is that the rate function that they can get, that these policies can get, is between I star of b minus 1 and I star of b. So it's nearly optimal. That's okay. And the other thing was the one what I told Armand, that in fact they actually picked the same realization. It also appears, the bad news is that from a rate function point of view, this greedy alpha, this, turns out to be not, does not have a rate function which is above 0, which is actually not surprising. We can talk offline why that's actually happened. But it actually still performs well in practice, and that's also not surprising. But we can maybe talk offline. There are some easy extensions and there are some not so easy extensions of this work. Okay, the easy extensions is that we can have the number of users to vary with the number of channels, not even by a constant. Okay, it can actually vary in different directions. But in this case, we'll need admission control rules. We can have multiple classes of users with different traffic statistics, but with the same on-channel probability and same delay requirement. That's easy to do. We can have channels with multiple rates. Actually is easy if you go from on to a multiple rate, to a very high rate. That's not a problem. But having different rates is a little bit harder, but we believe that's still doable. I think that's within the possibility of doing. For heterogeneous channel statistics and time correlation, I think finding the rate function delay optimality will be tough. But finding upper and lower bounds, like we did, I think is feasible. That's something we should be able to do. Okay. Then, of course, there are problems which are much more open, okay, which we don't have much of a handle on. Now you have many classes of users with not only different channel statistics, but also different delay requirements. That's, even how to handle that problem is unclear, because if you're looking at the worst delay, you'll just end up with the same result. You have to kind of be careful, as to how you can handle that. And of course, multi-cell coordination. This is the big question, right? So when you have interference now coming from the other users, that's not only manifested in this random kind of noise, right? You might have some more challenges and perhaps some ad hoc networking kinds of techniques. And then, look, we've looked at the large deviation rate function optimality, right? From a large deviation point of view. Delay optimality from this rate function point of view. Preferably, you might want to look at exact asymptotics, right? That's much harder. Or look at mean delays. That's also quite hard. So these are all kinds of open questions whether one can actually get mean delay optimality or optimality metrics. And maybe when we have that roundtable discussion, I can talk about some of the limitations of these other metrics. All right, thank you.
Thank you very much. So we have some time for one or two questions, and then remind you again, at 3 to 4 we'll have a round table, so you're welcome to come in this room again. Anybody has any questions?
What happens when the policy that does not have a rate function? So I guess in this case, you can still argue that you're on insurance principle.
Sure.
Do you lose anything? You can. In other words, are you? I mean, it's no problem in saying, look, I'm only playing with the ones
Sure.
that want to play with me.
Sure.
That's fine. But
Sure.
in the end, are you losing something? Because there's maybe one policy out there that people don't consider it, which seems to, in my view,
So let me think about this. So as long as the arrival processes, I think, are, I see what you're asking. So basically what you're saying is, can you have a policy that might give you perhaps better performance, even if a large deviation rate function doesn't exist for that person?
Well,
In the sense that it's sort of, the limb soup or something.
It may exist, but only in the sense you have.
Yeah, I
It
understand.
exists in the sense that the conjugation principle holds.
Correct. Right.
Because I mean, all the policies that you have are in a sense Markovian,
Sure.
which is essentially probably what you're using to prove that.
Even the throughput optimality part, remember, it requires some kind of Markovian principles, right?
Oh, yeah.
So, so the honest answer is I don't know.
Because you could argue that perhaps knowing a little bit about the task or using the task may be useful. Because
It could,
maybe not in the ID case, but in the case where you have an input that is Markovian.
Because it's memory, and you're hearing perfectly.
but I think, okay, so even if you use the past, let's see, if you use the past to make some predictions on the arrival processes, potential. I would, I have to think about that. Potentially, though, that could increase the complexity quite a bit, right? Because, but could be.
Any other questions? I have a burning question. Everything you did is one hop, right?
Yeah, cellular system.
So if I have two hops, no
Nothing.
prediction?
No predictions.
This is my burning problem.
Yeah. No, I mean, so there is this work, for example, that Venkat and Lynn have done in sort of the large deviation, large buffer asymptotics when you have multiple servers for the single channel case. The problem there was that because they were looking at large buffer asymptotics, they found that it was the sort of the convergence was very, very small.
Right.
And so they found some problems with that in practice. So you might have actually algorithms in practice that may not perform that well in that sense. I don't know if these same techniques can somehow be merged with those sorts of ideas and be looked at in a multi-hop setting. I haven't really thought about that. But that, I mean, if I was to do that, that's the first thing I'd look at. I'd basically look at how they did it for the large
We
one.
look,
And then see if we can match it with the model.
because here you have M servers and M users.
So the
It's not
problem,
the same time.
yeah, it's not a single. Well, look, even for the single channel problem, it was a very nice piece of work.
No problem.
But
I just can't use the word I'm
Yeah. So-
Anybody else questions? Yes,
Yeah, well,
that's the last question. Okay.
with different modulation and coding rate, you could have the server serve multiple packets of the same user.
you mean one server?
One server.
Yes. So because we were assuming that basically only one packet gets served by one, because what I assume that if the channel is on right now, that there is only one. But yeah, you can handle that case. So I think that case is, what I'm saying is that, okay, so the case that's relatively easy to handle is that when a channel is on, okay, it serves a fixed number of packets. Okay, that's easy to handle. The case that's more difficult to handle is when, because of multiple, multi-rate, that is depending on the channel, now you might be able to handle, say, K packets or N packets or something like that. I believe that is also still within the possibility of solving. That's what we are actually looking at right now. That's what the student is studying. I think that's doable. The one that's not doable, I shouldn't say not doable, the one that at least it's, I think, very hard to see a delay optimality result is when there is correlation in the channel. So when the channel is actually correlated in time, for proving delay optimality might be tough. But the bounds are such that I believe we can probably get a lower and an upper bound.
But delay optimization correlates are giving what exactly?
Nothing, basically right now we are assuming that the channel is IID, right?
No, but when you have correlation with the channel, what would be the definition?
Still, right, you need to come up with a scheduling algorithm, right, to get this delay optimality, right, in this sense.
Optimality means?
In the rate function.
Oh, the rate
in
function.
sense. Same, exactly,
Right.
the same metric.
Right.
We're not changing the metric.
Because statistics there may be
Yeah,
much more.
That I believe is much more difficult problem to have. Yeah, but although I will say that the multi-rate problem, when you have different rates, we haven't solved yet. So that's still something to work on.
Okay,
That's all.
less than 2 questions, Professor.